This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So next up is Kasper Cybin. So Kasper is a master's student from the University of Warsaw in Poland. He's doing research in the intersection of classical machine learning and quantum systems, mostly quantum phases of matter. And a very interesting thing about Kasper is he's actually a voice actor, with his most famous contribution being Russell in Pixar's movie Up. So go for it, Kasper.
Hi. Thank you for kind introduction and the opportunity to present here to you. Today, I want to tell you about an interpretable machine learning scheme we developed to extract the phase transitions and all the parameters associated with them. So that's a one-liner. Now the same thing in 10-ish slides. So imagine you have an experimental setup of a spin model you can prepare to be in different phases in the phase diagram. And you can make projective measurements of it, like snapshots. And wouldn't it be nice to just have something that would take your snapshots and tell you where are the phase transitions and the other parameters? Of course it would. In fact, this question is not new and it's known to be a hard problem, especially because the neural networks are known to be black box solutions and hard to interpret. But this problem has some real great proposals in the literature, especially interpretation.net and TetrisCNN that we are inspired a lot by. However, we believe that by standing on the shoulders of those giants, our proposal, TetrisCNN, can advance this problem greatly by reducing the computational complexity of the scheme and overall complexity, while retaining great results. So, let me tell you about how it works. Say you take those snapshots. In a regular scheme of analysis of neural networks, you would have a convolutional neural network where in one layer you have one fixed size of the kernels, and such a kernel, say here you define in PyTorch just a 3x1 kernel, can detect within its receptive field the magnetization, local energy, free-body correlations, or any combination thereof. But how do we know which of those correlations is actually doing the job, and which of those are redundant? And how do you know if the size you defined is actually enough to capture all that's interesting? So to tackle that, we propose to use not a single function, but a parallel, a bunch of parallel branches of convolutions where you have different shapes and sizes of those kernels. This way, you can have a greater pool of correlations that you sample, and you see which of those are relevant. And yeah, and then after global average pooling those, we combine them in the bottleneck, and we have achieved nothing so far because we still have lots of correlations and we have no way of knowing which of those are actually the meaningful ones. So in order to get an effective scheme of reducing this realm of possibilities, we L1 regularize this bottleneck and promote the use of simple kernels. And after slapping on some actual learning task at the end to get the place of the phase transition, we get a scheme that outputs you what is the most likely size and shape of the or the parameter associated with some phase transitions in the data you supplied. And we then here, we already have the main setting point, but if you like symbolic formulas, we have a treat for you, because we can also analyze this bottleneck and using symbolic regression, you can get an equation representing the knowledge distilled from the network. So, a high level overview how we do it. I have the data, says snapshots. we have the subnetwork that extracts the correlations from them, puts it in the bottleneck, and then the task network actually gets whatever we want from that bottleneck. And note here that this scheme is more or less task independent. So we believe that by varying the task, you can accommodate different problems. In what I'm presenting here, we use here a regression problem on the coupling value of the model, because that's a scheme that was shown to be working as an unsupervised detection scheme of phases. And yeah, just a quick recap on how it works, because this prediction-based method is, in general, that you have a continuous parameter that you make a regression on, and if there is no phase transition, as you sweep the phase space, you see no notable variation in the prediction error. However, if while sweeping the phase space, you get a phase transition, then there is a local extremum in the rate of error that you have, which is most notably seen as the local extremum in the derivative of predicted labels with respect to true labels. Yeah, and that's how you get the place of the phase transition. So that was the theoretical way how it works. Now let me tell you what it achieves. And you've seen this thing a lot of times before in this conference, but let me show you once again the transverse field Ising model. Here we'll take the Z and Y basis measurements and make this regression on the G parameter in Hamiltonian. You'll see in a second why the Y basis. Right, so the Z basis, the usual stuff. You know that there's the magnetization, that's the important part here, and the network soon enough knows it too, because right from the very beginning of the training, it picks up that it's the single body correlations, so that's the one-by-one kernel, branch with one-by-one kernels is the one that's contributing the most to the prediction, and all the others are zeroed out. So we expect then that in this data, it should be the a function of magnetization that's found as the activation. Now, in the Y basis of Ising model, the model would like to also try to get the single body correlations to be the meaningful ones, but there are no meaningful correlations in the magnetization, and it needs to move on to two-body correlations, which it does. And soon enough, it ends up with zeroing out all the other correlations and just leaves the two-body correlations as showcasing them as the most important. And knowing that, we can actually move on to this prediction-based method analysis. And as I promised, you look at the derivative of the predicted output with respect to true labels, and that's the red dots here. And it shows you really nicely where's the predicted phase transition. And that's the main thing you use. But we also noted that at the same time, it's even earlier in the architecture that the possibility of a phase transition is visible, because when you look just at the activations, you already see there this large variability, and the prediction of that, the derivative of that activation also indicates roughly the phase transition. So that's also a nice thing to know, that it coincides. And as I promised, we have the ability to extract the analytical approximation of what the network learned. So yeah, that's a cool feature. Also, a slide for the connoisseurs. We successfully also tackled a 2D Ising-Gauge theory model, which, roughly speaking, is a discrimination between a multiply degenerate ground state and a thermalized set of excited states. And in the generator of the system, you have a 2x2 you have two-bit correlations, like four-body correlations, and we actually see that the network picks up that it's within a 2x2 receptive field that the most meaningful correlations here are. So yeah, that's a great thing. I'm super happy to talk about it more if you are interested. And yeah, just to recap quickly, it's working, and I showed you here for the Ising model, but we also tackled the data from experiment onto the square Ising and X-ray model from group of Professor Antoine Brouet, and I'm also happy to talk about it more. Next, we want to tackle the non-rectangular lattices, because we know that there's some great stuff happening on Kagome and Ruby lattices, so we want to hop on that train and maybe address some of the non-localities that would be cool. And in the end, we would like to have a scheme that allows for an automated detection of phases and all the parameters just from the data, like my previous speaker described this idea. Yeah, so it was done under supervision of Anya David with our great collaborators James and Antoine. And if you're more interested in this, please check out our Units workshop paper and or the code. If you have any more questions, I'm happy to take them and answer, either now, later, or via mail. So, yeah, and then stay tuned for the next paper where we'll have the actual experimental results. So, thank you very much, and I'm happy to take questions.
Thank you very much, Kasper. So, time for questions. Yeah, Jamie.
So just to confirm, this is the convolutional neural network part, that's just done classically. You measure and then you classically
Yes, it's a classical network, and what we have is we have a quantum system from which we take data, but the whole scheme is like classical, just works on top of a quantum.
Have you considered, because I in my research, I look at doing convolutional algorithms inside a quantum system. So have you considered kind of just implementing everything within quantum? Because there are some speedups you can get. And
well, now that you said it would be really cool. We haven't, because what we wanted is a scheme that's like system agnostic, so we can here slap in data either from simulation, experiment, or whatever. But for the experiment itself, yeah, I think it would be cool. I'm happy to talk about it and maybe.
Yeah, definitely. That sounds good.
Right, brainstorm.
Thank you.
Thank you.
Other questions?
Thank you for a nice talk, Kasper. I am wondering if you have some bigger picture understanding what would be the main challenge in interpretability of this non-local order parameters. Is it like a computational issue, or is there some bigger underlying problem?
Yeah, thank you for the question. So far, the issues we have identified are that the receptive field of basically, we are limited by how large filters do you choose at the beginning. And we tried going to extreme sizes of the filters to actually get the very non-local correlations. But we are successful in doing it. It might work, but we think it might need some paradigm change on this stage to actually have branches with some different type of processing data to capture this global nature of some correlations and not just the local that we have from the several spin product. So I think that could solve some of the issues. Yeah, but I'm happy to suggestions. Open to suggestions. Yeah. We're really hoping on expanding it to the biggest number of possibilities. Thank you.
Any other questions? Well, if not, I think we can congratulate Kasper and let him know that he spoke like a physicist could understand him. So thank you, Kasper.
Thank you very much.